All right, let's say we have a mass hanging on a spring, and that mass is put into motion. We're not told exactly how it's put into motion, but we're given a velocity function for it. So let's say the velocity function is negative 5 pi sine of pi t, and then we're also told where the mass starts. We're told that the position at t equals 0 is 10. So let's find the position function, and then let's graph one period of that position function. So I want a function that gives me the position at any time t and matches up perfectly with this velocity function. Remember, the velocity is the rate of change of position. It's the derivative. So to find the position function, I can find the antiderivative of the velocity function. I'll start by doing that. To find that antiderivative, the negative 5 pi is just a constant out in front multiplied by the rest of the function. I know how to find the antiderivative of sine of t because I know the derivative of cosine t is negative sine t. But since the stuff in parentheses is not just t, I need to do something extra. I can either guess and check in my head, or I can just run a quick u substitution. I will go ahead and write out the u substitution. This is the reverse of the chain rule, remember, so I'm going to let u equal the function inside the other function. And then the derivative of u with respect to t will help me to solve for this dt. The derivative of u with respect to t is just pi. You may be able to solve this a little more quickly. That's fine. You can do it however you want. I'm going to solve for dt. So first, multiply both sides by dt. Divide by pi. And then I will plug that in here. And I'll replace pi times t with u. Then I'll just see what cancels and see if I can find the antiderivative after that. Since this is all multiplied together, this pi cancels with that 1 over pi. So I'm left with the antiderivative of negative 5 sine u du. Since the derivative of cosine u is negative sine u, I know this antiderivative will just be positive 5 cosine u. And then any constant could be added to that, and the derivative of the constant is 0. So anything of this form would have a derivative equal to negative 5 sine u du. Now let's go back and plug in what u was in terms of t. And that is our position function up to some constant. We don't know yet what this constant is. Could be 0, could be something else. I want to figure out what that constant function is, then I'll have the position function completely determined. And then I want to graph that position function. So to figure out what this is, I'm going to use the only other piece of information I have that I haven't used. And that is the fact that the initial position is 10. So if I plug in t equals 0 into both sides of this equation, then this s of 0 has to be 10. So I'm going to do that. Plug in t equals 0 to both sides of the equation. On the left I get s of 0, and I know that's equal to 10. On the right, when I plug in t equals 0, I get 5 times cosine of 0 plus c. Cosine of 0 is 1. So I get this equation, subtract 5 from both sides. It tells me C. So now I can update my position function. This C is equal to 5. So that's the main thing that I wanted to do. Now let's just graph this over one period of the function so we can get a better idea of how this motion is happening. All right. I have to remember what these different things do. I know what the cosine function looks like. Remember, cosine of 0 is 1, so the cosine function starts up here and then comes down. And it's periodic. It will just keep making this wave forever. It has a period of 2 pi. This maximum height is 1. This minimum height is -1. The midpoint is at pi. Having pi of t instead of just t will do something horizontally to this. It will either compress it horizontally or stretch it out horizontally. The 5 will stretch or compress vertically, and then this 5 takes all the y values that you would have had before, just adds 5 to them, so it just pushes them all up by 5. There are different ways to remember whether this pi compresses or stretches. One way to do this is, I know that for the regular cosine function, one period takes me out to 2 pi as the input for the function. So if I set this thing equal to 2 pi, that will tell me what value of t gets me to one full period of the graph. So I'm going to do that. I'll set pi times t equal to 2 pi. I know that determines the point where I reach a full period. So divide both sides by pi, get t equals 2. That means that for this function, the period is 2. This 5 is going to stretch out my function, so this wave will have an amplitude of 5 instead of 1. And then the plus 5 again will just push it up. So when I graph this, this will be stretched from -5 to 5, but then it'll be pushed up, so it'll go from 0 to 10. So I'm going to rescale this. I'll put 10 right here. 5. And then if I plug in 0 for t, cosine of 0 is 1, 5 times 1 is 5, plus 5 is 10. That starts me here. That's good, that's what I needed. I knew my initial position should be 10. From there, I know the cosine function goes down. It will come back up to a value of 10 once it hits the full period length, which is 2. So I know I'll have a point here. Then halfway in between is where it will hit its minimum. That's at t equals 1. I want to figure out where that minimum is. What's the y value, or the position there. So plug in 1 for t, you get cosine of pi. Cosine of pi is -1. 5 times -1 is -5. -5 plus 5 is 0. So the minimum of this function is here at 0. And now to graph this, I'm just going to make one period of a cosine wave that starts here and goes down here. That means it will be centered here at 5. So the position looks like this. Notice it will keep going like this. So it'll hit a minimum at 1, and then it will hit a minimum again at 3, and then again at 5, and hits a maximum at 0, 2, 4, and 6, and so on.